Hi, welcome back to this video on AI HPC infrastructure. So in this series of videos, we'll be talking about the last part, which is the GPU acceleration. So GPUs are the graphics processor unit. This technology has been used traditionally to actually accelerate 3D graphics in the past, but in the AI age, the same processing power that enabled 3D graphics has been used to accelerate a lot of mathematical computations that we need for things like neural networks. So that GPU or graphics processor unit enables us to process deep learning neural networks at a much faster speed than what we can do with our traditional CPU or central processing unit. So this topic is about GPU acceleration. So first of all, what is GPU? So it's also commonly called a GPGPU or General Purpose Computing on Graphics Processing Unit. This is the use of the graphics processing unit, which is typically used to handle computer graphics to perform computations in applications associated with things that are normally associated with the associated with the CPU. So one of these tasks would be actually the computations that is needed for AI, for things like neural networks. Now, the GPGPU pipeline were developed at the beginning of the 21st century, so around the year 2000, for graphics processing. For example, using what we call shaders, which we give you the look and the 3D effects within the graphics screen. Now, these same pipelines can be used to handle scientific computations, such as the ones needed for machine learning and deep neural networks. Since this kind of computational pipeline is highly optimized for this type of mathematical computations. So the history of it is that the general purpose computing on GPUs became practical and popular after the year 2000 with the advent of programmable shaders. So initially GPUs, the shaders are dedicated and is sort of baked into the hardware, so you can't reprogram it. But with the advent of reprogrammability within the shaders in the pipeline within the GPU, we can then actually use it for more general purpose computations. Notably, uh, what it really accelerates are problems involving matrix computations and vectors. Whether it's 1D, 2D, 3D, or 4D, or multiple dimensions, this really can be translated quite easily into the GPU pipeline, and the speed up is in the order of 10 to 20 times as compared with what you can observe on a normal central processing unit. So what are some of the implementations? So any language that allows the code running on the GPU to pull the GPU shader. So the CPU is still in use to run the general program, and what the GPU does is to accelerate the mathematical computations. So we can use the GPU as an add-on, right, as an accelerator, as a second processor, right, to actually accelerate those computations that is hardware is more purpose built for. But the most of the machine learning code is still running on the CPU itself, but the mathematically intensive parts are actually offloaded to the GPU. So some of the programming languages, it's not just the ones that's from NVIDIA. So for example, this standard-based ones called OpenCL. This is actually open standard defined by the group that also defined the OpenGL standard, so the Khronos group. So OpenCL maintains a cross-platform GPGPU platform, and it supports data parallel compute on the CPU. So OpenCL is actively supported by Intel, AMD, NVIDIA, and ARM platforms. And the Khronos group has standardized a specific programming language called Cycle or SCYCL, a high-level programming model for OpenCL as a single source domain-specific embedded language. This language Cycle is based on pure C++. The dominant platform, though, is not the open platform. So OpenCL is the open platform, so it's available on multiple implementations, on multiple CPUs and GPUs. But the dominant player in this space is actually NVIDIA. They produce graphics cards, but they also define the programming model called CUDA, CUDA, for this group of graphics cards. So NVIDIA actually launched CUDA way back in 2006, and it's a software development kit and application programming interface that allows the use of their hardware to code uh, those accelerated computations on their GPU hardware. So this particular slide shows us some of the differences that we would observe between a CPU and GPU. So it is not, you shouldn't be under the impression that the GPU is actually more powerful than the CPU. It's just that it is this is not really true. GPU is actually powerful only for certain mathematical operations. Whereas for the CPU unit, like your Intel or AMD processor, or the new Mac OS processor, right, the M1 processor, they are built for more general purpose computations. So they don't only do mathematics, but they can do a lot of other kind of computations very well. So a CPU or central processing unit works together with the GPU to increase the throughput of data and the number of concurrent applications or calculations within the application itself. GPUs were originally designed to create graphics images only, and for example in a computer game. But since the early 2010 or to 2000, GPUs are increasingly being used to accelerate calculations involving large amounts of data. So not just for the graphics processing unit, but what they can accelerate are those mathematical computations. A CPU can never fully be replaced by a GPU. So this is what I wanted to bring to your attention. A CPU is a more general processor. It can do a lot more things than what a GPU can. So we can never expect a GPU to completely replace the CPU. And in fact, if you try to replace the GPU, replace the CPU with a GPU, you'll find that actually the GPU would not be able to work as fast as the CPU when it tries to do general purpose tasks. Okay, so a GPU only merely complements the CPU architecture by allowing certain repetitive calculations within the application to be run in parallel and also to run very fast, okay, within the within the GPU pipeline. While the main program, the main machine learning algorithm still essentially runs on the CPU itself. Now, the main difference between the CPU and GPU architecture is that the CPU is actually designed to handle a wide range of tasks quickly, as measured by the CPU clock speed, but is limited in the number of parallel or concurrent tasks that can be running. So it cannot, the GPU is designed to actually render high resolution images and video, and is able to do all these computations in parallel, right? So it's able to handle a lot of parallel computations within the GPU pipeline. And because GPUs can perform these parallel operations on multiple sets of data, they are commonly used for non-graphical tasks such as machine learning and scientific computations as well. And designed with thousands of parallel simple cores to run simultaneously, GPUs enable massive parallelism where each core is focused on making efficient calculations, and these calculations are repeated very often. So the task that the GPU core can do is much simpler than what the CPU is designed for. But in the GPU, is able to do a lot of these simple tasks in parallel. So if you look at the hardware architecture, you can see that in the GPU, in the CPU, it has a huge amount of data space, and then the control also takes up the control of how the operations work within the CPU is taking quite a lot of it. So actually there's quite a bit of control circuitry inside there, and then the arithmetic computation is just one part of the chip. So you can see that a large part of the chip is just built to enable the GPU to perform many variety of different tasks in parallel. In the GPU, you don't see this variety of different blocks. In fact, most of it is just like the ALU, right? The computational units. It's just that lots and lots of computational units, and the control structures are actually very small part of the chip itself. So what this basically means is that I have a lot of uh, calculating entities within my GPU, and I can run a lot of calculations in parallel, right? But I cannot have very complicated programs running within my GPU, because the control portion, unlike the CPU, is just quite small. It doesn't really occupy a big amount of space on the chip itself. So you can see that GPU have the reason for being, and GPUs are merely complementing what the CPU has been designed for. So it's not meant to replace the CPU. So GPU versus CPU processing. So while GPUs can process data several orders of magnitude faster than the CPU due to the massive parallelism, GPUs are not as versatile as CPUs. So CPUs have large, broad instruction sets, managing every single combination of input and output of computer, which a GPU does not have the equivalent set. In a server environment, there may be just 24 to 48 very fast CPU cores, but when you compare this with GPU, the GPUs have thousands of cores. While an individual CPU core is faster as measured by the CPU clock speed, and smarter because there are more individual and smarter than the individual GPU cores as measured by the number of instructions. So the CPU generally is faster, and also has a much bigger instruction set as compared with the GPU core, which is slower and also has a more limited type of instructions or computations that you can do. The sheer number of GPU cores and the massive amount of parallelism that they offer more than makes up for this lower clock speed, as well as the more limited instruction set. The instruction set is actually the code, right, or the kind of task that the hardware can do within the CPU or GPU. So if you have a larger instruction set, there are more tasks that that particular hardware core can do. So what this translates to is that basically a CPU is more general. It can do a lot more different kinds of instructions or tasks as compared with the GPU cores. But there are many more GPU cores than the CPU core. GPUs are best suited for repetitive and highly parallel computing tasks. So beyond video rendering, actually GPUs are excellent at machine learning, financial simulations, and risk modeling, and many other scientific computations. So while in the years past, GPUs were also used for mining cryptocurrencies such as Bitcoin or Ethereum, increasingly GPUs have been replaced in the cryptocurrency space by more specialized hardware such as field programmable grid arrays or FPGAs, as well as ASICs. And this is also a trend in the AI acceleration space. So yes, GPUs can accelerate machine learning and are excellent at doing this, but you can also accelerate it using other dedicated hardware such as FPGAs or ASICs. And increasingly, we see AI processing units being designed and coming out as in a hardware form. So there will be purpose-built chips or ICs to accelerate AI computations beyond what we can achieve with GPUs. So currently, GPUs are still a major component in the industry in terms of accelerating AI tasks because besides they are already very optimized, and they can accelerate a wide variety of applications, but and using the same uh, uh, thing within the AI processing unit will make it run even faster and at a probably a lower cost. Uh, but what we actually give up would be the general purpose features of the GPU in being able to also render graphics very well. So we will lose some of that those features within those AI processing units. So there is a trade-off, right, between how much uh, dedicated features you want within the hardware versus the more general capability for a wider variety of applications. So of course this translates to scaling, right? So if you are able to handle a wider variety of tasks, you can create very high performance hardware but at a reasonable cost. Whereas if you have a very dedicated hardware, you may not be able to actually ship as many units of those, and therefore the cost of those units will go up, even though the speed is better. So this set of slides just talks about what I mentioned earlier. In the CPU, we have many different variety of blocks, right? Including a very large control structure. Then we have things, the ALU, which does the computations, and then we have a data space or the cache, and then we have the RAM as well. But in the GPU, you find that the computation units, there are many of them, and it's being repeated in the whole chip. So you can see that in the CPU, we can perform a variety of tasks because of the more various types of hardware units within this that makes it more flexible. But in the CPU, we can only do some tasks, but we have many units to actually do those tasks. So the control and the data section, this beige and blue section, they are also present in the GPU, but they are not as complex as what you have available on the CPU. So the GPU is less flexible than what the CPU can do, even at the hardware level. Now the GPU is built on the principle of more execution units, right? Instead of higher clock frequency to improve the performance. Comparing the GPU with the CPU, the GPU performs at much higher theoretical floating point operations of flops per second, and at a lower energy, right, with a higher energy efficiency because it actually consumes less energy. And the GPU relies on the higher memory bandwidth and fast context switching, executing the next level of threads to compensate for the lower frequency and to hide the memory latencies. CPU is excellent at performing sequential tasks with many if then else conditions or branches within the instructions stream of the CPU of the CPU. So it can basically perform a much more complex program with many switches in the stream of instructions that it's actually executing, and it does it at a high speed. And that diagram just now just shows this, that in the CPU, the control structure and the cache, they actually occupy a large part of the chip. This actually allows them to be able to excel at this. And the GPU puts much more resources than the CPU on the processing unit. So how is deep learning operation accelerated by GPU? So matrix computations, which are vector computations involving double precision floating point numbers. These are what the GPU pipeline can accelerate very well. And in fact, this is actually one of the major computations that we need in the deep learning neural network. Matrix computations to calculate how to actually do gradient descent, and also to accelerate the computations of adjusting the weights. Calculating all these values in parallel doesn't require faster process, just more of them, right? So more computation units. So GPUs basically developed for this, and therefore they're able to accelerate this type of computations very quickly. So when talking about parallel programming, one can actually classify into different types of or different classes of architecture. So we have the single instruction, single data. We have the single instruction, multiple data, multiple instruction, single data, and multiple instruction, multiple data. So in a multi-core CPU is basically a multi-instruction, multi-data structure, because each of the CPU cores is fairly independent of each other. and they can read in multiple instructions and multiple working on different data at the same time. So multi-instruction, multi-data, but GPUs are single instruction multi-data because the cores are actually repeating similar instructions. But we have multiple streams of data that is coming in the matrix. Deep learning is a problem in which SIMD or single instruction multiple data is actually well suited for. And when you are calculating the activations, the same operation, hence the single instruction, needs to be performed, but it's just that it's going to be performed with different data for each core or each of the GPU cores itself. So this is a blow up of that particular diagram just now. So you can see that there are many CUDA cores or GPU cores, and the control units, they do not occupy as much of the chip. Is what's being repeated is all those computational cores. So you imagine that if each of these cores is capable of helping with part of the matrix computation, for let's say for one layer, when you have so many different cores, we're able to compute many of the layers in parallel. So here's a warning. One of the very common programming constructs that people use in Python programming or any conventional programming language is a for loop, a while loop, or a do loop, a loop construct, a repeat construct. Now this kind of construct, while it's very convenient for the programmer to think in terms of a for loop, this basically ruins the parallelism in the GPU architecture, because we do not want to repeat the same sequence of instructions over and over again, even though we are operating on the different data. What we want to do is to be able to operate on many cells within your matrix, right, in parallel, rather than trying to iterate through one cell at a time. So this is just a warning. So generally try to avoid having a for loop or while loop or any sort of loop structure within your program if you want to take advantage of the parallelism within the GPU architecture. Okay, so Python libraries like Pandas and scikit-learn and even the TensorFlow, they inherently try to avoid you having to create a loop, unless you force it to actually and inject this into the program itself. Actually, there are constructs within those programming like frameworks to help you avoid trying to use a loop structure. So here's a warning. Please try to avoid using for loops within your program if you want to use that GPU acceleration. So NVIDIA A100, which is one of the recent NVIDIA GPU architectures, is just to show you that within this particular architecture, they are able to have many processing units, and more recently they have also created some additional representation of the floating point number, so that you do not just use the very high resolution floating point numbers, which are not really necessary for a very large neural network, because you can achieve the same results with a lower resolution. So this TF32 is actually to accelerate the math without having to lose the effectiveness, okay, of the floating point 32 structures, but not having to perform as many computations for this data structure. So it's a special data structure type and it's supported on this hardware. So besides just focusing on massive parallelism and having many repeating computation units, we can also play around with the representation or the binary representation of the numbers to get a more effective computation being done. So this is actually being trained on a mixed precision. So instead of just using a fixed type of floating point numbers, we can have a mixture of floating point 16 with lower resolution and floating point 32 wherever is necessary. So this strategy actually results in a significant reduction in the complexity of the computations, and hence the speed would improve. And also the memory and being occupied and the amount of transfer that you need in the memory bandwidth requirements will be significantly reduced as well when you use this kind of representation strategy for the floating point numbers. So this is the additional things that you can achieve with the hardware, and it's beyond just making massive repetition of the cores. Okay, so not just focusing on many cores, but also what the core, each of the individual cores can do in terms of making the calculation more precise but faster. So here's a quiz for you. So just pause the video after this and think about this, and before you go on to the next slide. So GPU accelerators are built to speed up all possible computations in the CPU, and it can be used to replace the CPU. So is this true or false? Here's another quiz. Okay, the secret to CPU acceleration of the AI model training is to have a massive number of transistors to enable fast and parallel execution of common mathematical operations such as the vector dot product, which is part of the matrix multiplication. Is this true or false? So again, just pause the video here and think about it before you think about the answer. And here are some references that you may refer to. So you can find references to the Docker part on containers and Kubernetes. And we can also find the hardware accelerated version of containers from NVIDIA, the NVIDIA Docker container. And there's also some studies that have been done to sort of compare different GPU frameworks like OpenCL with the CUDA. So thank you for your attention, and I'll see you in the next topic and this next set of videos.